We're now going to look at a class of series called alternating series. And we already know that this series here, 1 plus a half plus a third plus a fourth plus a fifth, this series, which is called the harmonic series, diverges. We've looked at this a few different ways. So this is the harmonic series. No, it diverges. But what if we looked at this series? 1 minus a half plus a third minus a fourth plus a fifth minus. This one is called the alternating harmonic series. And this guy actually converges. So these are built very similarly, but one is going to diverge and the other is going to converge. And we can kind of see why this one converges. I mean, you start at 1 and then you chip away a half, but then you add a third, chip away a fourth, add a fifth. So for a series to converge, that sequence of partial sums has to converge. And here we're getting partial sums that are sort of doing, a back and forth little dance, and really looks something like this. If we're going to add up, the first sum would be S sub 1 would be just 1. But then by the time we look at the second term and add these together, we go back a little bit. And so this time we're going back to 1 minus a half would get us back to a half. So this is our S sub 2. And then S sub 3 is going to add a third. So we're going right here. Not S sub 4, S sub 3. And then S sub 4 is this negative 1/4. I'm sorry, the A sub 4 is this negative 1/4, so we're going to take this sum and take away 1/4. And we just keep going like this, back and forth. And it is actually going to converge to the number natural log of 2. So this sum, and we'll write it this way, negative 1 to the n plus 1 of the harmonic series, n equals 1 to infinity. This series does converge to natural log of 2. And so what was going on up here with this guy? Well, here we were adding, if we're looking at the partial sums, the first one, we got to the number 1, and then we're going to add another half. And so we got to the second sum, and then we're going to add a third. And we're definitely adding a smaller amount each time. And the fourth one, we're going to add a quarter. But they just don't diminish enough. So this sum, once you're adding up this infinite list, it actually diverges to infinity. But this guy here is going back and forth, and it's going to converge to natural log of 2, the sums. So up until now, we've pretty much just focused on series with positive terms. And so in this section, we're going to really dive into what happens if you start getting positive and negative terms, specifically if they alternate between positive, negative, like in this pattern. What is it that we can say? Can we determine? Do they always converge? Do they sometimes diverge? So up until now, we've looked mostly at series with positive terms, and now that changes a little bit. Okay, so by definition, an alternating series is one whose terms alternate between positive and negative. So you'll often see this negative 1 raised to like the n plus 1, or sometimes the n, or sometimes the n minus 1. That's what's creating the plus minus plus minus. And then you have some term that could be really anything. So a couple things to be careful about. First of all, not all alternating series will converge. I mean, this one looks so nice, and you would think that they maybe all behave this way, but they don't. And then the second thing I'll say is that alternating series, even if they do converge, can behave weirdly sometimes. For example, in some alternating series, just rearranging the order of the terms can make the series add up to a different number. So you can theoretically, in fact, you can do it with this series, by rearranging terms, you can make this series add up to any number that you want. We're not going to go heavily into this, but we'll always assume that the series is going to keep the order that it's in. But this just gives you a flavor for that alternating series, when they converge, there's some strange stuff that can be happening. And actually, there's going to be different types of convergence with an alternating series. For a typical alternating series, there are 3 possibilities. The first possibility is that the series diverges. So an alternating series where this happens is 1, negative 1, plus 1. I'm sorry, 1 minus 1 plus 1, minus 1 plus 1, and so on. That's the page number there. And what's happening here is in this series, Here's 0, here's 1, and so the sum of the first term is 1, the sum of the first two terms is 0, the sum of the first three terms is 1, the sum of the first four terms is 0. These partial sums never converge, so the series cannot converge. It just keeps bouncing back and forth like this. The second possibility is that the series converges what's called conditionally. So converges, but conditionally. Just that word conditionally makes it sound like it's not that awesome, like there must be some sort of caveats to it. So the series that we were looking at just a minute ago, the alternating harmonic series, falls into this category. And so this equals 1 minus 1/2 plus a third minus a fourth. So it is going to converge, but it's going to converge what we call conditionally. I haven't even told you what that means yet. The third possibility is for an alternating series to converge absolutely, which makes it sound more sure and more kind of a stronger convergence than it is. And an example of the series that converges absolutely would be the alternating series 1 over n squared. So this is 1 minus a fourth plus a ninth minus 1/16 plus 1/25, and so on. So both of these converge, but one is a little bit of a stronger convergence. We'll talk about what that means. Okay, this is the alternating series test for convergence. If we have an alternating series here, and we've got this -1 to the n plus 1 power, that's creating the alternating sequence of plus minus, plus minus, plus minus, and then we have a term a sub n, and this a sub n is going to be positive or 0. Then if two conditions are met, the limit as n goes to infinity of each term is 0. So this sequence here is approaching 0. And the second condition is that the n plus 1th term is always less than or equal to the nth term for all n. So this is a decreasing function. If both of those conditions are met, then the alternating series is convergent. So that's pretty amazing because this condition was not enough just for a plain series. Think of the harmonic series. You know, this guy, definitely each term in the limit is approaching 0, but it's still a divergent function. But as soon as you add this to it, then the condition that this guy goes to 0 is enough to create this series to be a convergent series. So this condition was not enough for a non-alternating series, but it combined with this one is enough for an alternating series. Let's look at a couple examples. Okay, so this is the series that we've been given and asked to determine if this is a convergent series or not. And hopefully you can look at it and see that it is an alternating series. And so we'll use this test, and we're going to focus on, the positive parts of the series, or the terms of the series. So our first question is, let's just first get an idea of what this series looks like. This is if k equals 2, which is where we're supposed to start, then I get 1 over natural log of 2. And then if k equals 3, I get -1 over natural log of 3. If k is 4, I get +1 over natural log of 4. And so it keeps on going just like that, alternating 1 over the natural log of whatever term it is, +1. And so let's see, is condition 1 met in our alternating series test? Is the limit of these terms, just of the sequence, is that going to 0? Yes, these numbers, natural log of 2, natural log of 3, natural log of 4, those numbers are actually becoming bigger and bigger and bigger. And so 1 over the natural log of 2 is going to be larger than 1 over natural log of 3. And this down here is going to grow and grow and grow. It has infinite growth, and so we're going to approach 0. The sequence of this series is going to approach 0. Okay, so condition 1 is met. And is each successive term smaller than the one before in absolute value? And yes, each of these terms, this is smaller than this is smaller than this. So condition 2 is met as well. And so this series converges. Another example is let's look at the series k equals 1 to infinity of -1 k plus 1 of 2k over k plus 5. And so let's get a feel for what this looks like when k equals 1. That's going to be 2, 6. And then minus when k equals 2, 4 sevenths. And then plus when k equals 3, this will be 6 eighths. Minus 8 ninths. Plus 10 over 10. And so on. Okay, so then we go to our alternating series test and see if we can meet these conditions. This is an alternating series. So the first condition is the absolute value of these terms, the a sub n part, approaching 0. And it definitely looks like it's not. This is essentially 1/3. We're actually getting bigger with each step. This is 1. And so it looks like these are actually growing. So this condition is failing right off the bat. So we say the limit of our 2k over k plus 5 as k goes to infinity actually equals 2. This is not 0, which it needs to be, so we have a fail. So the alternating series test fails. And in fact, the series as an alternating series does not converge to 0. So I have to say that this test just determines convergence. It does not say, it's not conclusive that if this fails, then it has to be a divergent test. It just tells you, okay, if these two conditions aren't met, we can't use this test. We have to use some other way to determine. So the alternating series test fails, so we're going to look at the series as a whole, and we're going to try the divergence test from way back. The sequence itself does not converge to 0. So series diverges by the divergence test. Okay, at this point we're going to kind of drill into what did I mean by conditional convergence and absolute convergence. So let's talk about absolute convergence. Okay, I promised you that there were these different types of convergence, and absolute convergence is when if a series will converge absolutely if the series of the absolute value of its terms converges. And this is a very strong type of convergence. So we saw this when well, an example of this would be if you had the alternating series -1 to the n plus 1 over n squared. This converges absolutely because if you ignore the alternating plus minus and just take the absolute value each time of a term, then does this series here converge? And it does. We know that this is a p series where p is equal to 2, and so a p series with p equal to 2 will converge. If the series of the corresponding absolute values converges, then the series that we're looking at here converges absolutely. So this is a very strong type of convergence. And then the conditional convergence here is defined as if a series does converge, but it doesn't converge absolutely, then we call that conditional convergence, or it converges conditionally. And so an example of that would be the harmonic series and the, so let's see, this is this guy, and the harmonic series converges conditionally. Because if you take away the alternating part of it, then this series will not converge. This is a divergent series, but we've already shown that this series actually does converge. So if its corresponding absolute value series doesn't converge, then this guy gets to only converge conditionally. And so those are the two sort of poster boys for the different types of convergence. We have conditional convergence, and then we have this stronger absolute convergence. Okay, so this is the alternating series test. We see it at work right here where it proves an alternating series that's converging, and we see it here where the test failed. It was inconclusive, but then through another test, the divergence test, we were able to note that this series actually diverges, this alternating series. And then we have absolute convergence when this happens, and conditional convergence if that doesn't happen. Okay, so now we're going to go through a sort of a plan for testing alternating series for absolute and conditional convergence. First of all, somebody hands us a series and asks us to determine whether it's convergent or divergent. We look at it and we say, is it an alternating series? If it's not, then the alternating series test is not going to work. So we have to try a different test. It could be the, one of the comparison tests, either direct or limit, or maybe it's the ratio test. Or maybe we notice that it's a geometric series or a p-series, or maybe the divergence test right off the bat tells us that the series diverges. But if it is an alternating series, then the very first thing we do is actually test for absolute convergence. Because if it does absolutely converge, then we're done. We know that the alternating series converges and it converges absolutely. So we just test the series of the absolute value of each term. If absolute convergence does not work, then we test for conditional convergence. And conditional convergence we were just doing a minute ago. This works for any alternating series. We say, okay, do the positive parts of each term go towards zero? And are the terms decreasing? If both of those are true, then we have a conditionally convergent alternating series. This actually shouldn't be too hard to determine. You can usually look at the positive parts of the sequence and determine if they're going to zero. If this test is a no, then at this point the series may or may not converge. It probably won't converge, but this test becomes inconclusive and we have to use something else, like maybe a divergence test, to determine what's happening. So most of the time, either either this will happen or this will happen. Okay, so let's look at a bunch of examples. We're asked to determine the convergence or divergence of this series. It is an alternating series, and this is what's going on. We have a 1 over n times square root of n. So the first thing we do is we're going to test for absolute convergence. So absolute convergence. And that's essentially looking at this series 1 over n squared of n. So not the alternating part, just the regular positive part. And that n times square root of n, we know that that is n to the 3/2. And so this, we look and see what kind of series this is. Is it a geometric series, a p-series, or neither? This is definitely a p-series where our p is 3/2. So this is a p-series. That's always awesome because that makes things pretty quick. And not n, how about p equals 3/2? This is bigger than 1. So for a p-series, this converges as long as you're bigger than 1. And so this was the test for absolute convergence. Remember, you're just going to look at, well, what's the series if we just look at the absolute value of the terms? And it was convergent, so this larger series converges absolutely. So we're done testing. -1 to the n over n square root of n converges absolutely. Absolutely. Okay, awesome. So that was relatively quick. Let's try another example where we're going to look at the alternating series. And it looks like this. So why don't you pause the video and try this one on your own? You can probably look at it and tell some things already. Okay, we're going to test first for absolute convergence. And so we look at the series, just 1 over square root of n. This is 1 over n to the 1/2. This also is a p-series. This time p equals 1/2. That's less than 1, so this diverges. Okay, so we know that we're not going to have, I don't want to write that. We're not going to have absolute convergence, but we at least could go back and test for conditional convergence. And so at this point, we'll try the alternating series test. We just have to see if these two conditions are met. And if they are, then at least it converges conditionally. So we're going to test for conditional convergence. And we'll look at condition 1. It does the limit as n goes to infinity of 1 over the square root of n. So these positive parts of each term, does that go to 0? And yeah, it definitely goes to 0. So that first condition checks out. And then we have to ask, is each term smaller than the term before? So yeah, they're each getting, and we're just considering the positive parts. 1 over square root of n is getting smaller with each successive term. So this also checks out. Okay, so at least we have that this converges conditionally. It's too bad that it didn't converge absolutely. It's always nice to have a stronger condition, but at least we got the conditional convergence. Okay, one more example here. And we'll look at n equals 1 to infinity of this series. Even as I write it, you can probably tell what's going to happen here, but we'll go through the tests. First, we want to ask about absolute convergence. And this is where we essentially ignore this part of the series and say, okay, does this series converge? Well, this series without the alternating has a problem because it fails the divergence test. The divergence test asks, does your sequence go to 0? And this sequence, as n goes to infinity, is going to go to 2/3. So absolute convergence, 2n plus 1 over 3n plus 1. Well, let me say it like this. This goes to 2/3, which is not 0. So the absolute value series diverges. So fails the absolute convergence part. Let's try conditional convergence at least, maybe, hopefully. And we'll try our two conditions. We have to have that the terms are going to 0 and that each term is getting smaller. And unfortunately, a sub n is going to 2/3. Sort of already talked about this in the absolute convergence part of the test. And so condition 1 fails here. Okay, so the convergence test does not tell us that this series converges conditionally. We actually know that it diverges by the divergence test. So if you look at this sequence, this does not go to 0, so diverges by the divergence test. Divergence test. Okay, we've got an example of something that converges absolutely. We have something that converges conditionally, and we have an example of an alternating series that diverged. The last thing we're going to talk about is something called the alternating series estimation theorem. So often with series, we're not able to, we could say whether it converges or diverges, but we're not able to say if the series converges, what the sum is. We can with a geometric series, but with other series, it's often very difficult to find what they actually add up to, even if they do converge. But with alternating series, if we know an alternating series converges, we have a pretty good estimate, a way to find a good estimate for what the series is, at least getting close to what it is or as close as we want to. So let me tell you what this theorem says, and then we'll look at an example of how this could be helpful. So the first part of the theorem is the setup. If we have a series that looks like this. This is an alternating series because of this guy right here. If you have an alternating series that converges, this is a huge part of the theorem. This has to happen. And that has a sum that we'll call S. And S sub n, so remember we've used this notation before, this is the nth partial sum, will equal, equals 1 to n. So this is just describing that it is the nth partial sum of our series. Nothing has happened yet. This is just all still the setup. I'm just reminding us what S sub n means. Then, so this is the important part of the theorem, the sum of the whole series from 1 to infinity minus S sub n. So this is the sum of the whole series minus one of your partial sums. That difference in absolute value, so the difference between these two numbers, this real sum and this partial sum, is going to be less than or equal to, if this is the nth partial sum, it'll be less than or equal to the n plus 1th term of the sequence for that series. Written a little bit more elegantly, the real sum of the whole series minus the partial sum, that difference will be less than or equal to the n plus first term of the sequence. This looks like maybe it's not that awesome, but this is actually really helpful because this gives us a way. We may not be able to calculate the sum, but we can get pretty darn close by looking at partial sums. And this can tell us, if you want to be within 1/100th of the real answer, you just have to go out far enough and find that partial sum. And this is a bound on the error that we may be getting just from partial sums. Let's look at an example, and it might be even more clear. Okay, so here is the task that we're given. How many terms does it take to estimate the sum of the convergent alternating series, and here it is, to within 0.0001. So we may not be able to find the exact sum of this infinite series, but there is a way to get this close, within 0.0001, which that's a pretty good estimate, or we could even get closer if we took more terms. But the question is, how many terms does it take? And so they're really asking, for what n? How many partial sums out do we need to go? And this theorem is going to tell us. This theorem tells us that the difference between the real sum and any partial sum is just is less than or equal to the n plus first term. So we need to find, where is this term this size? And then that will answer our question, essentially. So we're going to answer this question. They say we want the difference between a partial sum and the actual sum of the series to be less than this amount. And so when does that happen? Well, that happens when so let's just find out first, when does some term of the sequence, when is, how about that? When is some a sub n less than or equal to this amount, this error bound? And a sub n, remember that a sub n is just the positive part of the series, and so that is just 1 over k to the fourth. And we're going to look at it for some particular n. So 1 over n to the fourth, we want this to be less than or equal to 0.0001. And so we're going to solve this inequality. So 1 is less than or equal to 0.0001 n to the fourth. And so that is also n to the fourth. And then dividing by 1 divided by 0.0001. So how about 10,000? All I did was just divide both sides by 0.001. And so then we'll take the fourth root of both sides. But this one we can do even without a calculator, but we could, just to double check, the fourth root of 10,000 is 10. So 10 is less than or equal to n. So for n greater than or equal to 10, then a sub n will be less than 0.0001. And so if we take n equal to 10, then the ninth partial sum should be plenty. Okay, so I want to run through this logic of the problem one more time. They ask us to find a partial sum that's within 0.0001 of the real sum. This expression right here is just a mathematical way of saying that the partial sum is within 0.001 of the real sum. But this looks an awful lot like this guy from our estimation theorem. And so we're going to ask, okay, when is, for what term of the series, not the partial sum, but just what term of the series are we guaranteed to be less than or equal to 0.001? And so all of this work in here was just done to find that n that satisfies this inequality. And it turns out that if n is greater than or equal to 10, then all of those terms are, A10, A11, A12, all of those will be less than 0.001. And so let me actually write it like this here. So we know a sub 10 is less than 0.0001. So s minus s9 is going to, because of this theorem, will be less than a sub 10. S minus S9 is less than or equal to a sub 10. A sub 10 is less than 0.001. So if we have the ninth partial sum, that's guaranteed to be within 0.001 of the real sum. This is nice. These alternating series, if you have a convergent alternating series, then you know that each successive term is getting smaller, they're tending towards 0, and so it does make it easier to through a partial sum, get closer and closer in a pretty exact way to the real sum. So the answer to the question that they ask is it takes 9 terms. At s sub 9, this is within 0.0001 of the real sum. So that's a pretty good error bound. So our big ideas are definitely how to tell if an alternating series is converging or diverging, and this was totally new, the 2 different types of convergence, conditionally or absolutely. And it's also possible for an alternating series to diverge. And then we also have this really handy theorem of being able to not find out what the sum of the series is, but get as close as we want to through an estimate of a partial sum.